Hey, Dr. Clark coming at you with another differential equations video. This time we're in section 3.3, modeling with systems of differential equations. Let's take a look. What we're going to look at this time is a second order differential equation. And that is we're going to derive a system for a spring mass problem and see how the methods of systems of differential equations can apply to it. What we mean is you've got some mass here. Let's say it's on a spring, for example, and so that mass is going to kind of oscillate up and down as it's on the spring. Here you've got gravity pulling it down, so we often will orient it horizontally so the spring sort of oscillates left and right. Then you've got a sliding friction you can incorporate, but there's no gravity in the system, so it will just kind of sit there if it's at equilibrium. You can also hook up a damper to it. You can hook up the spring there. You can apply an external force. So this, sometimes this will be a spring mass damper system with forcing term. This is really where we're trying to get to. And we're going to spend a lot of time this semester playing with differential equations like this. To get there, let's start with Hooke's law. If you know what Hooke's law says, it's that the force on a spring, is equal to negative kx, where x is that displacement from equilibrium. That is, if you've got a spring and you've stretched it out, let's say normally 0 is equilibrium if you kind of like doobity-doobity-doo, that's where it likes to be. You've stretched it. Well, the further you stretch it, we'll call that x of t, the stretch from 0. Stretch from 0. X is the displacement from equilibrium. Then the force is proportional to the stretch. So if you stretch it a little bit, it pulls a little bit. If you stretch it a lot of it, it pulls a lot of it. The other thing I want you to notice is that negative right there. It is in the opposite direction. If you pull to the right, the spring pulls to the left. If you push it in, the spring pushes back, right? So if you compress a spring by pushing that mass from 0 to the left, the force is to the right. Okay? So in other words, the force of the spring is equal to negative kx, where x is equal to displacement from equilibrium. That's Hooke's law. Then we've got Newton's second law. Of course, you know it. F equals ma. All right? Classic. F equals ma. Now, what about F equals ma? Well, what's a? A is the derivative of velocity. And what's velocity? Velocity is the derivative of position, in this case, x of t, the position on the x-axis, right? We're on the x-axis, there's 0, and then it moved over here to x of t. It's at a new position to the right. So x of t is position, okay? Its first derivative is velocity. The second derivative would be acceleration. So that acceleration is x double prime, okay? So then if we put these together, we would have mx double prime equals negative kx. And then if you divide by m, you get this differential equation right here. It's second order. It's a second order differential equation. X double prime equals negative k over mx. We assume the mass is not 0. Otherwise, you've got yourself a problem anyway. So there we go. We just derived a differential equation for a spring. Okay, this would be a situation with no friction because all we did was modeled that spring force. So we didn't actually get to anything else. Okay, now I said we were going to talk about systems. How is this a system? We'll check this out. We have x double prime equals negative kx. That's second order. We can turn it into a system by the following. We already know that x prime equals v. Okay, and we know that x double prime is equal to v prime. See, x double prime equals v prime. equals A, right? So what we do is we replace this with V prime right here. So that comes down. This becomes V prime. That goes there. We get V prime equals negative kx. And x prime equals v. That's just the definition of velocity. X prime equals v, velocity, right? Now you've got a system where x is equal to position and v is equal to velocity. It's a system in position and velocity, okay? Now you can analyze that. We haven't learned how to solve systems yet. We will, but we've just constructed a model, okay? And it's kind of cute that a second order differential equation became a system of two first order differential equations. Isn't that kind of nice? Okay. Now, what if you got friction? Okay. So let's say you've got your spring mass, boobity boobity boo. It's going like that. Let's pretend it's in a tank of water or something. And as that mass slides back and forth, it plows through the water and sloshes that water on. Well, that's going to be a friction force. Or you could imagine a situation where you've hooked up a damper, okay, to it. So it's on a spring, but also it's got this little damper, and that pushes through and slows it down, kind of like on a shock absorber on a car. If you've ever looked at a car suspension, you've got a big old spring and you got a big old shock in there. Well, that's a spring mass damper setup, basically. So if you think this isn't useful, you've never driven in a car. So this is exactly what gets used in those situations. So how would we set up the friction term, right? How would friction work in one of these situations? Well, I'll tell you, we just slap on a friction term right here. So we take this is the old one we had, this is the new. So this is the old, this is the new hotness right here. And the only difference is this negative BV. So let's see what that says. It says that the friction term is proportional to velocity. So think about that. If you've got that little damper in there and it's not moving, it doesn't generate any force. It only generates friction when it's moving, okay? So that's the idea, is friction is only in the case when there is a velocity, when there is actual movement. It's the movement that generates the friction. If you drag something across the floor, you only hear a noise when you're pulling it. It's only that friction acting when you're pulling it. Otherwise, it's just sitting there, right? We assume the friction is proportional to velocity, and also it's in the opposite direction. If you're moving this way, if V is, say, positive, which way is the friction? It's the other way, right? If you're pushing through the air is pushing back on you. You know, have you ever ridden a bike in the wind? Okay. You're pushing the air is pushing you. You feel the resistance of that force. That's why that's why it's negative right here. So the acceleration is in the opposite direction of velocity. That should make sense if you've ever ridden a bike in the wind, that the friction force is opposite of velocity. Well, now we got a real system because we got x's, we got v's, we got x's, we got v's, we got x's in the v equation, we got v's in the x equation. We got it, it's a big old system. So this is kind of an interesting little guy there, but yeah, that's basically how a spring mass system would work. Okay, so that's it. So we've constructed from scratch a system that models a spring mass problem, and it is a system. Okay, we're going to do one more problem here, the radioactive decay series. Now this is, I just stole this from Wikipedia, but this basically shows you how elements decay over time. So you can see you've got uranium here. It decays into protactinium. Protactinium decays into actinium. Actinium decays into francium. Francium into acetine. But eventually you get down here to the bottom, and if you look at what this is, it's lead. Okay? There's the lead, right? And so everything turns into lead eventually. Okay, that's the idea of radioactive decay. These radioactive elements all eventually basically turn into lead, stable lead-82 here. Radium, yes, here's the radium series. So I think the red is the radium. Yeah, so the red one, you'll notice you get to radon right here. That's radon gas. That's in your basement. And the problem with radon gas is it starts out as radium in the ground, or maybe uranium in the ground at one point. But radium in the ground turns into bismuth. Bismuth turns into radon. Now it's a gas. Now it comes into your air. You breathe it in, and then it radioactively decays while it's inside your lungs. Well, now you've got inside of your lungs astatine in your lungs. Then that decays. You got polonium in your lungs. You like polonium? I didn't think so. Then pretty soon you got lead in your lungs, right? That's no good. So these radioactive decay series, very interesting. These are bucket problems, okay? Every one of these things is a bucket, and it's buckets on buckets on buckets on buckets, because the neptunium is dripping into the uranium, and the radium is dripping into the protactinium, and the protactinium is dripping into the thorium, and everything drips down, and then eventually at the bottom you got lead. And then the lead bucket basically just fills up until, all these radioactive elements are gone. And so there's lots of cool math you can do this, dating rocks and all kinds of things based on sort of radioactive decay series. But it's also a real situation with, radon gas in the ground and that kind of thing. But they're big old bucket problems, basically. And we're going to just do a real, an easy one to kind of give you an idea of how this works. So let's say X turns into Y and Y turns into Z. So just a three sequence here. X of T, Y of T, Z of T are the representative masses. Lambda X, lambda Y, lambda Z, the decay rates. So X is just radioactive decay. All right, X is just radioactive decay. But X turns into Y, which means every time you lose an X, you're going to gain a Y. So the decay of X is an increase into the Y term. Okay? But then the Y term, well, that's going to radioactive decay as well. So lambda YY. So the Y has radioactive decay right here, but it also is gaining this X there. And then Z, well, what's Z? Well, dZ dt is, well, every time you lost a Y, you gained a Z, right? So it's sort of conservation of mass, right? You lost a Y, you gained a Z. So these derivatives kind of have to add up to zero, basically. Otherwise, mass would be created and destroyed. And then if Z is stable, then maybe the thing ends there. If Z isn't stable, then you can keep going. And this is the crazy thing about one of these is it's actually solvable, because you can essentially solve X of T, and you can say, well, X of T is just X naught e to the negative lambda X T, right? This is this differential equation, this exponential decay differential equation, has this as its solution. Well, then you can take that as a solution and put it in for X, which means it's a function of T. Well, now this is a function of T. It acts as a forcing term, and this becomes a linear differential equation, which you can then solve for Y. Now, Y of T is a big old mess because it's got, it's not just exponential decay, it's got the forcing term. But you can solve it, and then you can take that solution and stick it in here and solve that to get to Z. And if you do that, you get these nice graphs. I think this is just the slides that kind of just saying what we just did. But you can get these cool graphs where X is in red. So here's X. X is in red. It's going down to 0. And then X's, they turn into blue, which is X is turning into Y. So the Y's are decaying, but they kind of decay more slowly. and then those turn into z's, and so you can actually see the z's going up as the x's go down. So just think about this. We lost 3 grams of x, and the y went up by 3 grams in the same amount of time, right? So all of those x's turned into y's, and all the y's turned into z's right there. But eventually, if the x's and the y's are basically almost gone, then the z runs out. And I just kind of ran this in the computer with different numbers so you could kind of get a sense. This is lambda x 0.2, lambda y 0.08, lambda z 0.01. The y decay rate is much faster than the x decay rate, 4 times as fast. So the y's end up going away once they get created by x. They just go and turn into z right away. But the z decay rate is smaller, so z has time to build up before it kind of goes back down. In this case, z is not stable. Up here, we assumed that z was stable, in which case, if that was the case, the z graph would have looked like this. It would have just leveled off after all the x and z were gone. 5 plus 2 is 7. You would have had like 7 grams of z, basically. But in this case, I set z to also decay, and so the z ran away as well. And so that's kind of a nice example of using exponential decay, but as a system of multiple elements, one turning into the next, turning into the next. Okay? And I think that is basically all I had. So we saw a couple different systems, and hopefully you got a sense of how these systems of differential equations can be created. You'll notice we didn't solve any of them. They're much harder to solve in general. You can write them down as a model, but a lot of times systems have to be solved with a computer, either numerically or some other way. So, here I've just drawn a graph of the answer. I haven't actually calculated it. We technically could in this case, but it would be a big old mess, and it's not really worth the time to do it on here. So hopefully you got a sense for what systems are, and we'll see you in the next video. So have a good day.